So how do we determine whether or not a molecule is aromatic? Well, we have rules to determine whether or not a molecule is aromatic. The first rule is that the molecule has to be cyclic, right? So it has to be a ring structure. The second rule is that the molecule must be fully conjugated. Now this sometimes gives students a little bit hard time. What does fully conjugated mean? In essence, it means that all atoms in the ring must have a p orbital, right? Each atom has to have a p orbital. The third rule is that the molecule must be planar. And I like to think of rule number 2 and 3 as kind of going hand in hand because in order for a molecule to be fully conjugated, those p orbitals have to overlap, right? So we have to understand for conjugation, P overlap has to be maximized. And the last rule is that the molecule must contain 4n plus 2 pi electrons. And so what you do is, in essence, you add up all of the pi electrons only, understanding that each pi bond contains 2 electrons, and so it should be relatively easy to add up the number of electrons. You set that number equal to 4n plus 2. And when you solve for n, if n is a whole integer, 0, 1, 2, 3, etc., then this rule is satisfied. And this is called Huckel's rule. Let's look at some examples. Here I have, this is Z135 hexatriene. And this particular structure is actually planar, right? All of the carbons are sp2 hybridized, and so it's a completely planar structure. So we have trigonal planar geometry at all carbons. It's also fully conjugated, right? Because all of the carbons are sp2 hybridized, so they all have a p orbital available to them. If you count the number of electrons, we have 3 pi bonds. So 3 times 2 is 6. We have 6 pi electrons. When you plug that into the equation, 4n plus 2 equals 6, and you solve for n, you get n equal 1, which means that it satisfies Huckel's rule as well. However, it's not cyclic, right? So it's missing one of the 4 fundamental rules. And because it's not cyclic, it cannot be aromatic. Okay, here we have cycloheptatriene, right? Cycloheptatriene is cyclic. However, if we look pretty, kind of closely at this structure, we see, I hope fairly quickly, it's not fully conjugated. Why do I say that? Well, because this particular carbon is sp3 hybridized, which means it does not have an empty or a p orbital available to it, right? And so that complete conjugation is stopped at that carbon. And therefore, cycloheptatriene is not aromatic. What about this scenario? This is called cyclobutadiene. Cyclobutadiene is cyclic. It's also planar. It's fully conjugated because all of the carbons are sp2 hybridized, right? So they all have p orbitals available to them. So how many pi electrons does it have? Well, it has 4 pi electrons, right? 2 pi bonds, 2 times 2 is 4 pi electrons. And when I plug this into Huckel's equation, 4n plus 2 is 4, n equals 1/2. And therefore, even though the first 3 rules are attained, the last one is not. And so cyclobutadiene is not aromatic. And as a matter of fact, we see this playing out in that it's a very reactive species. And we're going to determine, kind of why that is in just a little bit. Now, one of the things that we might want to ask ourselves is, well, is there an easy way to um, look at stability of structures? And one way is by drawing what are called frost circles, right? So a frost circle is, we call, a quick way to determine the number of molecular orbitals in a particular structure and the relative energy of each orbital in that molecule. The way we construct a frost circle is we inscribe a polygon, which has the same number of sides as our cyclic molecule, into a circle. And that circle has a radius of 2 beta, right? So 2 beta would be beta would be an arbitrary energy value. The key is that we have to inscribe that polygon with its vertex pointing down. And so when we do that, we can look at the intersection of the polygon with the circle. And at each intersection, that marks an orbital position. Let's take a look at the frost circle of benzene. So here we have benzene. We see that benzene is a hexagon. And so we're going to construct a frost circle. So we draw a circle, and in essence, that the intersection of that circle um, uh, denotes essentially the energy of one p orbital, right? We inscribe the hexagon into the circle. Notice the vertex is pointing down, so we have a point at the bottom. And in this way, in essence, we're always going to have one orbital that has the lowest energy. Now, if the p orbitals were not interacting, we'd say this is a non-bonding interaction. And so where the vertexes of the hexagon intercept, this creates bonds. And the radius is 2 beta. So I have a bond here, and then I have a bond here and here, right? This is where they're intersecting. And then I have 3 more above that non-bonding plane. So you see fairly quickly that I have my lowest orbital is 2 beta, right, or negative 2 beta. And then I have 2 degenerate orbitals, each one with an energy of negative 1 beta. And these are my bonding orbitals. And this is very similar to what we described the molecular orbitals of benzene looks like, right? So the frost circle kind of is an easy way to actually determine the structure of those orbitals and their relative energies. I have 3 bonding orbitals and I have 3 antibonding orbitals. And I know that when I look at benzene, I can count its number of electrons. I see it has 6 electrons, so I add those 6 electrons to the lowest orbitals, and voila. I get something that looks like the molecular orbital diagram of benzene, and that's exactly what it is. So I can do this with butadiene, and we saw that butadiene was not aromatic, right? The structure of butadiene is this, and I can construct a frost circle. So I said, we start out kind of with the same setup. We start out with a ring, we intersect that ring, and that's the non-bonding. So if there's any vertices that intersect at that position, we say that that's a non-bonding orbital. And so when we inscribe butadiene, notice we inscribe it again, vertex down. And we see that indeed we're going to now have 2 orbitals that are non-bonding orbitals, right? So we can draw our orbitals in. We see we get 4 orbitals. So with benzene we have 6, with butadiene we have 4 orbitals. Here I have 1 bonding orbital, and I have 1 antibonding orbital, and I have 2 non-bonding orbitals. And again, that distance, the radius is 2 beta. All right, so how many electrons do I have with butadiene? Well, I have, remember, 4 pi electrons. The 2 are going to go at the lowest energy, and then, based on Hund's rule, 1 electron goes, we have 2 electrons that are degenerate. They're both non-bonding. So 1 electron goes in one orbital, the other electron goes into the second orbital. And we see that it's a diradical, and indeed butadiene behaves like a diradical. So this is why it's very reactive. Again, notice 4n electrons, or 4 electrons, and if I instead use 4n as my equation instead of 4n plus 2, n equals 1. When you have this type of scenario where all of the rules are satisfied and you have 4n pi electrons, this is what we refer to as anti-aromatic. Typically, anti-aromatic species are very reactive. Let's look at cyclooctatetrene. Here's the structure of cyclooctatetrene, right? It's an 8-membered ring. It has 4 pi bonds, which means it has 8 pi electrons. And when I construct the frost circle of this, again, remember I have to inscribe that, that polygon with a vertex pointing down. And so when I do that, I get this, right? So 8 sides, vertex pointing down. I draw in my orbitals where the vertex is touching the circle, and I get, again, so I get 8 orbitals. 3 of them are bonding orbitals, 2 of them are degenerate non-bonding orbitals, and then 3 of them are antibonding orbitals. How many electrons do I have in this system? I have 8 electrons, 8 pi electrons, right? So I add those 8 electrons in to go to the lowest energy, and then I have 4 going into the second lowest energy, so that's a total of 6. And so I have 2 left over. Again, one goes into a non-bonding orbital, the other goes into a degenerate non-bonding orbital. So in this particular example, we see that it looks at first glance very similar to butadiene in that it should behave as a diradical if it satisfies all of the other requirements, being cyclic, planar, and conjugated, right? So it's conjugated, it's cyclic. Notice if it's planar, it's going to be a diradical. It happens that it's not planar. And so in order to alleviate this instability, it actually distorts. And the structure of cyclooctatetrene looks like this. And so you see that it's no longer planar, and it really behaves like a normal, typical conjugated tetraene. Not, it doesn't have that special stability of an aromatic compound. So, one of the quick things that we can check based on our rules, we know right away that it's not aromatic. Why? Because it only has 8 pi electrons, and when you look at Huckel's rule, it doesn't satisfy Huckel's rule at all, and therefore we wouldn't even expect it to be aromatic. But the frost circle right away tells us that it shouldn't be stable. It should not be aromatic. So how can we predict aromaticity? This is one of the things that chemists really sometimes love to do, right? We love to take a molecule and say, well, if it only had this feature, maybe it would be aromatic. And one of those types of molecules happens to be cyclopentadiene. If we look at the structure of cyclopentadiene, we see that it's cyclic. It's obviously not aromatic, right, because it has an sp3 hybridized carbon, right? So it's right away we know it's not aromatic, right, because of that, the CH2 group. Now, if we do some chemistry on it by removing a proton from that CH2 group, well, then the carbon becomes sp2 hybridized and it becomes an anion. So if I highlight the two hydrogens coming off of that sp3 carbon, and I think about what I can do with that. If I remove a proton, that means it's an acid. So if I take a base and I abstract a hydrogen, a proton from that base, where the electrons go to the ring, I should in theory be able to make something that at least is cyclic and conjugated, right? Because that carbon is sp2 hybridized now. And so it should be pretty easy to remove that proton. And indeed, if you look at the pKa, that pKa is 15. So what does that mean? Well, remember the pKa of water is 15.7. And so this happens to be more acidic than water. And indeed, slightly more acidic than water. And indeed, if I take potassium hydroxide and I react it with cyclopentadiene, I can get this structure, right? So that the conjugate base, the anion, cyclopentadienyl anion. So notice this happens to be planar, it's cyclic, and it's fully conjugated because now that carbon is sp2 hybridized, right? So if we have to assume that that carbon is sp2 hybridized. And of course, that is an assumption because it's a carbanion. We typically think of carbanions as actually being sp3 hybridized. But again, there's this driving force of aromaticity because if it is sp2 hybridized, then the pair of electrons have to reside in a p orbital, right? And so now that makes it fully conjugated. How many electrons do we have? We have 4 electrons from the pi bonds plus the 2 electrons from the anion, and that gives us 6 pi electrons. So 6 pi electrons satisfies Huckel's rule, right? So let's think about drawing the Frost circle of the cyclopentadienyl anion. Again, we start off with our circle. We draw the pentagon in that circle, again with the vertex pointing down. And we get 5 orbitals. 3 of them are bonding orbitals, 2 of them are non-bonding orbitals. And the 3 bonding orbitals have 6 pi electrons. Notice they're lower in energy than your isolated pi orbital. And again, it's very characteristic of and very similar to the structure of benzene, right? Where you have all 3 bonding orbitals filled. And so we draw cyclopentadienyl anion like this, right? Where you have essentially a pentagon, and there's a negative charge. We draw the circle in the ring, right? And we place a negative charge in that circle, denoting it's an anion. And we see that the cyclopentadienyl anion is much more stable than typical carbanions. And as a matter of fact, we can draw resonance structures of the anion itself, right? Donating a pair of electrons into the ring and moving a pair of pi electrons up to an isolated carbon, and the resulting resonance form looks like this. And of course you can see that I can do this again, and I get another resonance structure, another unique resonance structure. But again, I can do it again, and I get another resonance structure, right? And I can do it again, and I get a fifth resonance structure. In essence, all of the carbons have a slight negative charge to them. So that negative charge is distributed to all five carbons in that ring. And because of all of the resonance structures, we see the cyclopentadienyl anion being very stable. Okay, so let's look at cycloheptatriene. Again, it's not aromatic, right? Why? Because of the sp3 carbon. Now, cycloheptatriene, its chemistry happens to be unique in that it can donate a hydride. So it's not having a proton removed, it's actually donating a hydride, so a hydrogen plus 2 electrons. And we know that cycloheptatriene will readily react with electrophiles. Here's a reaction with the triphenylmethyl carbocation. So this is triphenylmethyl tetrafluoroborate, and if I highlight the two hydrogens on that sp3 carbon, I can take and I can donate a hydride to that carbocation. So I'm taking the electrons and the hydrogen, right, going to that carbocation. The resulting structure is a new carbocation. And this is the cycloheptatrienyl carbocation. It actually has a special name called the tropylium ion. So this is tropylium tetrafluoroborate. And now we see that what once was an sp3 carbon is now an sp2 carbon. It's a carbocation. So now it has an empty p orbital. All of the carbons in the ring have p orbitals, right? So it's fully conjugated. It has 6 pi electrons in that fully conjugated system, and we can think about the frost circle for this, right? Again, drawing the vertex pointing down, we get this. So we have 7 orbitals that are produced. 3 of them are bonding, 4 of them are antibonding, no non-bonding orbitals. But again, I have 6 pi electrons, right? And so when I think about those 6 pi electrons, where are those electrons going to go? They're going to go to the lowest energy, as we've seen before, and so they all fill all of the bonding orbitals. Hence, aromatic.